Alright, so in class today we started this definition that energy is the ability to do work, and doing work means making something move. In the lab, the falling marble made the clay move outward, leaving a crater. And in this video we're going to learn specifically what gravitational potential energy is. So here we see some data from group 4, and they had as their independent variable the drop height, and their dependent variable was crater width. So this is their data here, and we can see that the data actually, it doesn't appear to be exactly linear, and that might be expected given some of the physics behind how the ball interacts with the clay. But we can see that as the height increases, the crater width increases. So the amount of work done on the clay is increasing. Therefore, we're saying that the energy that the ball had, the potential energy, was directly proportional to the drop height. And here's another group showing that the work done on the clay is directly proportional to the height that it was dropped from. So this energy we're going to call potential energy, or gravitational potential energy, we see is directly proportional to the height that it was dropped from. And we know that because of the shape of the graph, looking like this, because we had height here on the horizontal, and essentially work done in creating the crater on the vertical, and we see a straight line. And if we look at the data shared by group 2 today in class, where they varied the mass, we can see that the mass was also directly proportional to the work done on the clay. Therefore, we can also say that potential energy is directly proportional to the mass of the object. And we know this because of the shape of the graph there, where we were changing the mass and looking at the work done, or the crater size, and we also saw a linear relationship. So far we can take these two things, we can combine them together. We can say that potential energy is proportional to both of those, so that's going to mean mass times height. So if we were to double the height, it would have double the energy, double the ability to do work. If we double the mass of the ball, we would also get double the energy. And there is one other component which Kyle mentioned, that we could change the gravitational acceleration of the ball by doing it on a different planet. And that could also affect how much work that ball would do on the clay when it hits. So there's one more element here, we could change g. And remember, by g we mean 9.8 meters per second square on Earth. So if we did this same lab on the moon, would you expect to see larger or smaller craters? Hopefully you recognize that it would be smaller craters. It's not going to be hitting the surface of the moon, which moving as fast, it won't have the ability to do as much work. Okay, so if we use this set of units here, where we have kilograms for mass and meters for height and meters per second square, we'll just go ahead and put it in G. We usually don't really do any calculations with potential energy on other planets. If we're using those units together, then we get a unit called a joule. And that word is spelled J-O-U-L-E, named after some guy in the 1800s that was super involved with developing steam engines. And actually, I should probably not write 9.8 there, because what we're saying here is that a joule is equivalent to a kilogram times meter square, because we have the meter times meter, over second square, and that second square is from over here. So that's the basic definition for a joule. Going back to this equation here, as long as we are using those units, then we can replace this proportionality with just a straight up equal sign. Potential energy equals mass times height times g. If you try to use, say, pounds instead of kilograms, you're not going to get joules. Or if you try to use centimeters, you're going to get centijoules. So let's go ahead and add this definition under what we just wrote. Gravitational potential energy, PE, of an object is directly proportional to its height, mass, and gravitational acceleration. which is 9.8 meters per second square on Earth. So let's try this example. You should add this to your notes. What is the gravitational potential energy of a 1,000 kilogram wrecking ball that is pulled back to a height of 12 meters? So I made a little diagram here, and you should make a diagram similar to this in your notes. Here it is, the wrecking ball at the bottom. Here's the wrecking ball pulled up. So the height of 12 meters is how much higher it is pulled up compared to when it was at the bottom. And I'm carefully measuring that height from the same point of the wrecking ball. And at this point here, we can do a little math. Potential energy equals mgh. So this is a 1,000 kilogram wrecking ball. G is 9.8 meters per second square. The height of it is 12 meters. So calculating that out, we get 117,600 joules. It would also be good practice to write up here the mass equals 1,000 kilograms. So we're getting all of our information on the page like that. So you can use this example to do some of the practice problems that I assigned for homework. See you in class. Have a great evening.